Welcome to a screencast on using bond energies to calculate reaction enthalpy. And for this, we'll use the example using bond dissociation energies to calculate the enthalpy change for the reaction for the complete combustion of propane, C3H8. So propane reacts with oxygen to make CO2 and H2O. And to be able to use bond dissociation energies to calculate energy change or enthalpy change for a reaction, we first need to know what bonds are broken and what bonds are formed, so we need to draw the Lewis dot structures. Propane C3H8 would have this Lewis dot structure. Oxygen has this Lewis dot structure, a double bond between the two O's. Note there are 5 oxygens on the left side of this equation, and those are our reactants. And what's going to happen to make the products is the carbon-carbon bonds and the carbon-hydrogen bonds in propane will break. The oxygen-oxygen double bond in the O2 molecule will break. And then CO2 will be made. It has this Lewis dot structure, 2 double bonds from carbon to oxygen. And then, of course, water, H2O, has this Lewis dot structure, 2 single bonds from oxygen to hydrogen. Those are our products, and these bonds will have to form. Note that there are 3 CO2s produced, so we're going to have 2 carbon-oxygen double bonds per molecule times 3 molecules, so that'll be a total of 6 carbon-oxygen double bonds formed. And then for water, we have 2 hydrogen-oxygen single bonds per molecule. We have 4 molecules, so that's going to be a total of 8 oxygen-hydrogen bonds that are formed. And then we also need to recall that when bonds are broken, energy is taken in, energy is required to break bonds, and when bonds are formed, energy is released or energy is given off. So the values to break these bonds will be positive numbers. The values corresponding to these bonds when they are formed will be negative numbers. Now, of course, we get these numbers from an appropriate table of bond energies. There's carbon-carbon, 345 kilojoules per mole to break the carbon-carbon single bond. Carbon-hydrogen, 415 kilojoules per mole to break 1 mole of those bonds. Oxygen-oxygen double bond, 498 kilojoules per mole. Carbon-oxygen double bond, 741 kilojoules per mole. And oxygen-hydrogen single bond, 464 kilojoules per mole. So those are our values. And now we'll go back to our molecules and note that we are going to be breaking 1, 2 carbon-carbon single bonds per propane molecule. And we're going to be breaking 1, 2, 3, 4, 5, 6, 7, 8 carbon-hydrogen single bonds in a propane molecule. And then we'll be breaking 1 oxygen-oxygen double bond per oxygen molecule, but there are going to be 5 molecules, so we're going to break 5 oxygen-oxygen double bonds. And our values for that are 2 times 345 is the carbon-carbon single bonds. 8 times 415 is the carbon-hydrogen single bonds. And then 5 times 498, all of these are kilojoules, for the oxygen-oxygen double bond. Those are all positive values because energy is required or taken in to break bonds. Now for the products, carbon dioxide, we have a carbon-oxygen double bond, 2 of them per molecule, and then 3 molecules, so that's going to be 6 total. And then for water, we have hydrogen-oxygen single bond, 2 of those per molecule, times 4 molecules is 8 total, and those values are 741 kilojoules for the carbon-oxygen double bond, and then there's 6 of those, and 464 kilojoules for the hydrogen-oxygen single bond, and there's 8 of those. We have negative signs indicating that energy is given off when these bonds form. And then we just simply combine the amount of energy needed to break the bonds with the amount of energy given off when the bonds are formed. That gives us our total. And the total amount of energy to break all of these bonds is 6,500 kilojoules. It's a positive number. The total amount of energy given off in forming these bonds is negative 8158 kilojoules. It's a negative number, of course. And then the total of those is negative 1658 kilojoules for this reaction, for the complete combustion of propane. Now note, getting a value using bond energies to calculate the enthalpy of reaction is going to be approximate because bond energies are average values for a particular type of bond. They're not going to be as accurate as using delta H of formations. And technically, bond enthalpies are for gas phase molecules only, so we're a little bit limited both in our accuracy and what we can directly apply this to, but it's a very good, useful method to get approximate reaction energies for quite a number of reactions. And that's it for the bond energy and reaction enthalpy calculation screencast.